I want to sort of give you a demo of my time machine, which is what I sometimes call it, my time traveling debugger, and
Mm-hmm.
and I want to try to explain how that works, because I feel like nobody else in the world understands how it works other than me. The source code, if you ever care to look at it, is github.com/airportyh/playlang. It's playlang because I called it the play programming language. It's a very basic programming language, kind of like JavaScript or Python.
Mm-hmm.
It doesn't have a lot of features. For example, it doesn't have classes and objects and methods and stuff like. It doesn't have any OOP in it. It's just a very very basic language. It's like JavaScript without the objects, kind of. It does have
So,
it does have dictionaries, but just like basic
mhm.
dictionaries, not objects and methods. So I'll do an example. So like I'll show you a piece of code.
When you design it, do you want it to be more like functional?
Um, in one of the other languages I did, but this one I didn't care. This one actually it started as another programming language where I did want it to be functional, but it was that one was called the fun programming language. But that one I wanted it to make it so that the there's a subtle way in which you can say this function is pure function and this function is not a pure function, and the language
Mm-hmm.
will know in which context it is, and it will automatically enforce for you the pureness as needed.
Gotcha.
That was the idea of that one, and then but I forked that one basically to this one because
Mm-hmm.
I wanted to focus all my energy on this debugger concept, and then
Mm-hmm.
I kind of removed the part about the pure functions in this one just to simplify it so that I have less work every time I decide to add a feature.
Gotcha.
Yeah. So anyway, so this is a tic tac toe game that I made. It's a terminal based game. Uh,
Mm-hmm.
the So I decided that every program is gonna have a main function, which is gonna be your entry point.
Mm-hmm.
C also requires that, and then this game is just like while true. You can play more than one game, hence the while true, and then you play a game, and then after the game
Mm-hmm.
is done, you ask them, "Do you want to play again?" Right? And then we have a play game function. There's a tic tac toe board. You're gonna draw the board, and then you're gonna ask the human to move, check if there's a winner, or check if the current player is the winner. And then if he's the winner, you're gonna say that's the winner, and then game over is gonna break out of this while loop. Otherwise, you check for
Mm-hmm.
draws. There's a one 1 second delay here. Sleep. I don't even
Mm-hmm.
know whether this is necessary. And then I have this smart computer. I implemented this AI based on the
Okay.
Minimax algorithm. Um,
Mm-hmm.
and then you check for a winner again, and then you go again, go back to the human move, and so forth. So this is the basic program. Obviously, there's some more functions. I'm gonna run this program. This is tic tac toe term. There was a previous version that's DOM based that ran on a web page, but in this version, I'm running it in a terminal.
Mm-hmm.
Okay, so this is like your move, and you select one of these squares, basically.
Okay.
So which square do you want to choose?
Let's do 5.
Okay, let's do. Oh, I
Right.
have this timer to tell you the time
Uh-huh.
because I'm working on performance, and my time traveling logging stuff causes this to be slower than it otherwise would be. So currently it took
Mm-hmm.
like 2.3 seconds for the computer to think. What move do you want to make now?
Let's do 2.
2 is here, right?
Right.
Okay. All right. He blocks. Now what do you
Oh
want to do?
no. Okay, let's do 3.
Right here.
Uh-huh.
He blocks there. Where do you want to go now?
Okay. Let's do 4.
4. Oh, the computer won. He had a double attack.
Nice.
Okay.
Oh yeah, that's good. Okay.
It's pretty smart, right?
Cool.
I mean,
Yeah.
first game you're not warmed up, but still, like you can tell there's an AI playing, right? Now I want to show you the time traveling debugger. So as a result of playing that game, it logged all of the game state, like every snapshot of the program. It logged to a file, and that file is it's going to be the name of the program dot history. So tic-tac-toe term dot history. I'm working on 2 different database backends for this history file. So currently I have the SQLite version where the data is stored in a SQLite database. I'm also working on using LevelDB, which is a popular low-level embedded database.
So you're trying different ones because of the performance, because you have large amount of data.
Yep. That's one of the big reasons. There's multiple metrics about performance that I care about. One of them is how fast can the logging occur so that I slow down the program minimally.
Gotcha.
The other thing is, I want to utilize the disk minimally as well. And then the final one is like, well, once you get the data in there, the querying it has to be reasonably fast as well for the debugger to render stuff. But I think the third one is the least hard. Like getting the debugger to read the data is the least performance intensive of the 3 problems. But anyway, so we're gonna browse the data. So basically, there are these snapshots. So currently, there are that many snapshots that were taken during the execution of this program. Each snapshot has an ID. It has a fun call ID, which is a ID of a function call that was made. Every function call that is made inside the program is also logged in this fun call table. And it has the name of the function, the parameters that were passed to the function. This is an ID because it links to an object in the object table. The object table contains all the objects that were ever created in the program, and the parameters is an object that is like a dictionary that has a name and value of the parameters that were passed to this function for this instance of the function call. And then the parent ID is the parent function call of this function call. Somebody called your function within another function. So this ID is the parent function, the function call of the parent function.
Yes, you can function.
You can actually see that because the call to the play game function, its parent is 1, which is a call to the main function. Yeah. And then the objects look like this. So this is the object ID, and then this notation is a extended version of JSON, which gives you references. So whenever you see star and then a number, that's a reference to the object in this table with that ID.
That's cool.
Yep. So that's how the database is structured, at least for SQLite. Gonna run the Zoom debugger.
How do you handle asynchronous stuff? Like, or
in the programming language?
Yeah, I guess in the programming language, and also in the debugger, is there?
I use async await implicitly. When the compiler compiles this program, it converts it into JavaScript, and that JavaScript looks like this. This is the source code itself. I saved it to a variable called code so that the debugger later on has access to the source code itself. So this doesn't matter. The real JavaScript that it got translated to, all the functions are async. So even though they're not async in the actual programming language, they're all async when generated as JavaScript. And anytime you call a function, you await it.
Oh, okay.
Always. Always. So that way you don't have to. I don't know. There might be drawbacks to this approach, but this is just a prototype. I'm just trying different things out. So I decided to take this approach.
Gotcha.
But what's nice about that is like Node.js is very, very heavily asynchronous environment. Like everything that's I/O that you do in Node.js is async, and this, like, even asking for the user to type in something and then hit enter, that's asynchronous as well. So we can just await that now, and it can just be, it just seems like a normal function where we're like, oh, prompt, and then you'll get the answer right away.
Gotcha.
Yeah, so this is much simpler to learn. It's kind of like Python. So that's the asynchronous aspect. Let's see. Oh, what's going on? Oh, I forgot to start the history API server. So there's a backend REST API that I've implemented in Node.js, and I'll just briefly show you that server. And it's kind of ghetto right now. I'm hard coding the name of the history file in here that to be served up. We could make that a parameter, but I haven't bothered to. So now I think I should be able to run this debugger. There we go. So you've seen this before. This is a deep zoom debugger. We're looking at the main function like a box, and if you zoom in close enough, you can see the source code, and also you can see the intermediate values of the program as it's evaluating stuff. So we can drill into play game, and then you can actually get a high level overview of what happened in the game. You can kind of make out what happened in the game by looking at the board, the state of the board at each turn, right? Initially the board is all empty, and then the human made a move, and you chose this move, 5. That's that in the center. It would be nicer if this were laid out like a grid. but it's not. It's an array. And then the computer went here, and then you went here, and then the computer went here, and you went here, and so forth. I think this scheme for debugger is pretty cool because you can, at a glance, you can get an overview of what happened in the game at a high level. And
that if it's a loop, so that you can see loop like flat in a flat way.
Yeah, which is quite different from a normal debugger experience. In the way that I imagine it, I'm like, I hope this actually, gets adopted, and then there's actual people using it for production work. And the way I imagine this would be beneficial is usually you're looking for that one spot where something went wrong, different from your expectation, right? But there's different levels of granularity to what that spot is. It could be like the line very, very deep down in the call stack. There's one line that caused the problem, but you can also look at it as a higher level. Like if you're playing a tic-tac-toe game, you don't have to necessarily drill down to the deepest level, but if you're looking at a high level like this, you can tell when there's one move that seems out of place, right? Maybe the human, after this human made a move, something just looks wrong. Or after the computer made that move, something just looks wrong. And then if you saw something fishy, then you would know to drill down to that step.
Yeah, that makes sense. Well, what if the person, instead of writing a loop, the person write like something that using recursion instead of loop, then that will mean we can't do something like this, or
Uh,
because we speak nature of recursion.
I'll show you what that looks like because the AI does use recursion.
Okay.
So like that's the smart computer calculate move. That's the AI,
Mm-hmm.
and that's a recursive function.
Okay.
And I don't know if my mind is sharp enough to try to explain minimax. We don't even have to know exactly how minimax algorithm works to sort of get a high level understanding of what it's doing here, because
Mm-hmm.
you can see the shape of this thing. You can see it's making these recursive calls to itself in here,
Right.
right?
Uh-huh.
And it's making a whole bunch of them. This is 1, 2, 3, 4, 5, 6. It made 6 recursive calls to itself, which I think
Uh-huh.
it makes sense. It's about the middle-ish of the game that I zoomed in.
Mm-hmm.
So maybe it like move 4 or something like that. So there's like 6 squares left that it could choose. So it's trying all the
Ah.
possibilities. Here it's actually trying to calculate the opponent's move here, I believe.
Mm.
Yeah, it's like given that I am me, which I'm X here,
Mm-hmm.
it's like switch player to figure out who the opponent is. The opponent is O. Given this board, it's imagining a new board where I am going to move to this I, which is gonna be 2. So I moved to 2, which is here. So where me is X here. So imagine if I moved here. Now I'm gonna calculate the computer's next move for my opponent. Like if I
Mm-hmm.
moved here, what would my opponent do? That's what that does. And now I could drill into that guy
Mm-hmm.
and see the calculations there as well. So I think you
So
still.
what is the that?
What's the depth? Let me see. It's only 3. I think I made it 3 so that it wouldn't try as hard, but I could do 4 or 5. When I
So the
do.
depth is levels you're trying, and then you're just like trying each one out,
Yeah.
and then to figure out which one is
Yeah, like if I go here and then what would you do? And then as you, I'm thinking, well, if I did this, what would you do? But only up to 3 levels.
Mhm.
And that's more or less how people play chess or something like that. But people are much less efficient than the computer, or much more error prone than a computer at doing this. That's a demo of what this is. But the real thing I wanted to do is more to explain to you how this works, how this was implemented. Because there's a lot there, how about we just try to do an overview this time?
Sure.
Okay.
Mm-hmm.
So first, there's a compiler. So given the code, which is written in the Play programming language, the syntax of the language is like a cross between Python and JavaScript, kind of, or
Yeah.
Ruby. Like I at one point I used fun. Yeah, I might switch back to that because I kind of like writing the word fun all over the place. I didn't use Python's indentation thing, but I still just use brackets. But I decided to not use JavaScript's curly brackets because I decided they are noisy, too much visual noise, and I prefer this square bracket, which is like cleaner looking. Uh,
Okay.
yeah. And then other than that, if statements do not require parentheses around the conditional. And other than that, this is like a programming language you're used to. There's no innovation about this programming language. I wrote a compiler which translates this code into JavaScript. I think I'm gonna call
Okay.
it JavaScript star because even though it's normal JavaScript is 100% runnable JavaScript, you can easily translate this code to JavaScript by just changing the syntax a little bit here and there, right?
Mm-hmm.
But that's not the code that the compiler is translating to because there's this immutability that's built in to the system. All the mutation that this JavaScript performs are immutable.
How do you translate something that is mutable to an immutable? Like, say, if I just want to assign things to a variable later, then how do you? Okay.
I'll talk about that. Even though this code that's written at the beginning is mutable, can very well be mutable. After it generates this JavaScript code, all of the code is immutable. And then we have this logger that's embedded in this code. And this logger is gonna log all the immutable state into a database. And then after this logger logs the information to the database, we have this. I implemented 2 different debuggers, and the one I showed you is the Zoom debugger. Zoom debugger is this web-based, canvas-based user interface that's gonna be driven from the data from the database. But as I mentioned, I also have a API, history API, that's surfing the information from the database for the use of the debugger. History API is reading information from the DB, sending it to the Zoom debugger in an on-demand basis. And then the Zoom debugger is rendering this visual that you were seeing. There's also a step debugger, because I do want to give that option as well, like a traditional step debugger that's also going to read from this history API. So that's more or less the high-level overview of how this stuff works. If we could break the compiler down to like parser, AST, code generator as well. But that's more or less the overview.
So did you write the parser?
Yep.
Yeah, so did you write the parser in the AST and the code generator yourself, or you were using like a...
I used this tool called Nearly.js. It gives you a handy way of writing a parser. You can write the grammar. We worked on a project where we use a thing called peg.js. This is similar to that. It's also possible to write your own parser by hand. I've also done that before. But this one, I'm using this tool.
Gotcha. Well, yeah, you mentioned the step debugger, because you have all this immutability stuff, so I assume the step debugger can make you able to like go back.
Yeah, so you can look at it as the information that is stored inside the database. And by the way, this is partially inspired by Redux. Remember, in Redux, we have this concept of the timeline. And then every time you make a change to the app, you have like a reducer that produces the next state of the app based on the previous state of the app. So we have like state 1, state 2, state 3, etc. That's how the data is stored in the database. For me, it's snapshot 1, snapshot 2, snapshot 3, etc. Right? So in order to implement the step debugger would fetch a particular snapshot, and each snapshot is a particular point in time. So if you hit next, it just have to move to the next snapshot in the database.
Gotcha.
If you want to drill down into the function call, you would still just move to the next snapshot, because the snapshots are based on lines of code. So if the code is going to go into a function call, the snapshots are going to start getting taken within the nested function. If you want to skip a function, then you can write logic, which that's what the step debugger would have to do. You would write logic. You say, I'm going to continue to advance the snapshot until, like if the next snapshot has a taller stack frame than my current stack frame, that means the next statement is in a nested function, right?
Yeah, I get the idea.
Yeah, so you just keep advancing the snapshots until your stack frame is back to the same height as what you started with, and then you get to skip the function call.
Okay, so it's pretty much like a tree of like each stack, and then the stack has children stack.
Yeah. So I can talk a little bit about this middle bubble. How can you take a mutable code and convert it into immutable code? A lot of that is like coming from what we already know about functional programming. It's like, well, if you're not allowed to modify an object, then how do you modify an object? Well, you create a new object that's like a copy of that old object, except you modify this one thing about it, right? Say you have your program is like x equals 1, and then we're gonna mutate it to 2. What am I gonna do?
Right.
In a normal programming language, this information is stored in the stack frame, right? So if you have a function f, then we're creating a stack frame for this particular call of function f, and this stack frame is gonna store the values of its variables. So initially, we're gonna put a 1 in it. Once it reaches this line, we're gonna erase it and put a 2 in it.
Right.
So the way I make that immutable is I represent, instead of using the system's stack frame mechanism, which JavaScript itself has stack frames built in, I don't use that. I made a synthetic stack frame. And my synthetic stack frame is represented as a JavaScript object. I need to remember the name of the function call, so I have a fun name. I need to represent the parameters that were passed in. Well, you could skip that actually. You could, so I'm not gonna include it. But you definitely need the variable, and that can just be represented as a dictionary that contains the values of the variables, right? So let's say I represent the stack frame like this. Well, except if you have another frame underneath it, like f calls g, and then there's more stuff, you need another one of these, right? So you can either use an array or a linked list. At one point I used an array, now I've switched to linked list. It's cheaper to modify things with a linked list than an array. When you want to modify an array, you have to create a brand new array every single time and copy all the things over to that array. If it's just a linked list, then you're just modifying the head of the thing. So I do so I do it as a linked list now. G's parent is f actually. So this frame becomes the parent of another frame. There's gonna be another frame. The function name is g, and then it will have its own variables, blah blah blah, and it will also have a parent that happens to be pointing at that. So if you can represent the stack as objects, then you can mutate that object in an immutable way, right? You just, instead of changing the value here, you just make a new version of the object. You can reuse the bits that didn't change, but then the bits that did change, you have it point to a new value.
So in this case, do you create a new object for this frame?
Yeah. I would have to create a new one of these and a new one of these. If there's other variables, I would have to copy them over in here and then just change this one, right?
Okay, so another question. How do you have the unique identifier to say, hey, I want to go back to when x is...
Okay, so the unique identifier is a auto-incrementing ID, like a database would do if you had an auto-incrementing ID.
Okay, so if you see like a mutation, you will create another thing with
exactly
the new ID.
Yeah. So yeah, and I'll show you some of the code that's making this stuff work. So these are the next ID counters that's generating the new unique identifiers for these database objects. So instead of doing it in the database, I do it in the program itself, because that way I don't have to ask the database for what the next ID is, and then the logger can just be faster because it doesn't have to wait on the database. It can generate its own IDs. So if we looked at, let's search for where that gets modified. So that gets modified whenever we call this log new object method, which is part of the logger. So I have this logger guy. I have multiple implementations of the logger. There's a null logger, which does not log. But we have the SQLite logger. All of them have the same API. When do we log a new object? This is push frame. Guess what push frame is? Push frame happens when you call a function. It pushes a new frame onto that stack of frames. So it makes sense that we need to, because we're generating a new variables object to contain the new variables, and we need another object for the new frame as well. So this is exactly what that is happening. And then the way I implement a linked list is actually with an array of length 2. No, the first one is this frame. The next one is another array of size 2. That's how I implemented linked list.
Okay, what is the $sign stack?
$sign stack is the current stack. So during the execution of the program itself, whenever a function call is called, we have to modify the stack, and then $stack is always the current stack.
Oh, okay. Gotcha. Okay, so you basically just like add a new layer.
Yeah, exactly.
New frame.
Inversely, we have pop frame, which is gonna take that. Like I said, the first item in the array is the current frame, so it gets the current frame, and it does some cleanup. The cleanup is another thing I need to talk to you about. That concerns garbage collection and automatic reference counting. So that will be an interesting topic for another time. But basically, it removes it. The stack is now the second thing in that array now, which is like the parent stack. So we just popped it. But more or less, that's how immutability works. We should try to talk about garbage collection and automatic reference counting at some point. This is something I want to talk about because a lot of developers maybe are not aware of these things happening, and also you might not have a program in a programming language that does not have these things in it.